Today's lecture is meant to be discuss the heterotic string, the world sheet theory of the heterotic string in a little more systematically in more detail. But in order to do that, we're going to need a diversion. We're going to first have to have a little diversion to remind ourselves. Mainly, this part will be mainly notational about Lie algebras, and then we will have a small discussion on current algebras. Okay, so let's first remind ourselves about Lie algebras. As I said, this part will be largely about notation, since all of you know about Lie algebras, but just you may not all have the same notation. Okay, so if we have a Lie algebra, it's got some generators. We call those generators TA and TB. And they obey the commutation relations FABC, TC. Now let's see if there's an I, there's an I. Okay, great. Now, you know, the fact that the Lie algebra, that the group multiplication law is associative, is reflected in the fact that these T's obey the Jacobi identity. Because the Jacobi identity is a trivial identity for matrices. You expand it out, it's just true. But this leads to associativity of the group multiplication law. And the Jacobi identity is what? It's the following statement: TA, TB, TC, and then plus cyclic. So let's say plus TB, TC, TA, plus TC, commutator TA, TB is equal to 0. Hey. For any three matrices A, B, and C, this thing is just an identity. You just open it out and you'll see it's true. Okay, so this by itself has no content, some triviality, but it gets content when we know that TA, TB is of this form. Because then what we can do is put this in here. So we get TA, and then we get commutator F, B, C, D, TD, plus three other terms. Now let's work out what this term was. This term was F, B, C, D, and this was F, A, D, F, A, D, let's say M, T, M. All these other three, those other two terms are similar. They're just related by cyclically permuting A, B, and C. Okay, and so we conclude that this quantity cyclically permuted in A, B, and C for all with D contracted but M left free has to be 0. Okay, and this is a consequence of this Jacobi identity. Okay, now one thing to say immediately is the following. As you all know, there is a representation. There is a representation of the group which is basically given by commutation. So TA is represented on the group matrices, on the generator matrices themselves, and the action is given by commutation. Okay, so commutation here is generated by this matrix. So in this case, the representation matrix for TA. Okay, so suppose we have suppose the convention is a representation matrix acts with an I or not. Let's say we'll make our convention. Is T in some representation R, A with an I, let's say, Mn acting on zeta n. There are some elements, some basis of a Hilbert space, but the basis of representation. It acts as these matrices. Okay, In this case, the elements themselves were the T's. The matrices were these TAs. So this particular representation TA, in this particular representation, which as you know is called the adjoint representation. Okay, in the adjoint representation, we identified this as FA, and then the matrix indices are Mn. And I might be messing up people's standard conventions of having an I or not. At least with my definition, I have no I. Okay, so this is one particular representation. Every group has the adjoint representation. The matrices are represented by these Fs. And this statement and this statement here is, now if you know, because of antisymmetry, AB, this is clearly antisymmetric with respect to NB. So this we could pull here up to a minus sign, since we're going to get 0, it doesn't matter. So this statement can be thought of as TB adjoint. Now, yeah, and TA adjoint. TB adjoint, TA adjoint, and these two are free indices, so that's good. TB adjoint, TA adjoint, and
commutative structure, it's TA times TB acting on TC.
What?
On the first line. Second line, the Jacobi identity. First TB acts on TC, and then TA acts on this quantity.
Right. So you want to write it that way, you're saying.
So TA in adjoint acting on TB in adjoint.
Sounds good. TA and adjoint, there's no commutator, just T A acting on TB, and then we have in Indranil's way of doing it, we've got CM. Okay, this for the adjoint representation, if you take this and completely cyclically symmetrize under A, B, and C, we get 0. That's one way of viewing this this relationship here. The fact that these two completely symmetrized give 0 is that statement. Okay, now let's keep going. Right.
Was it trace normalization you were using?
Exactly. I'm going to try to use. This is largely why I'm going through this exercise, because I want to use all his conventions. Okay. 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 So now, okay, what we do now is define a positive definite inner product. Okay, so on the space of the generators of the, so at the moment, you know, we've got these generators. These generators belong to some vector space. Okay, there's no natural normalization in them. You can choose any basis elements A, B, and C. Nothing particular has been used. Okay, now what we're going to do is a little more. We're going to endow this vector space of generators with a norm, with an inner product. Okay, so we define some inner product which is of the form TATB is equal to DAB. Okay. Now, this norm is going to be defined so that it's invariant under group action. That is, if I take my T's and I rotate them by adjoint action, okay, then the new rotated T's have the same inner product as the old T's. Now, what we've done is to define what the small change in t's is, right? We've done infinitesimals. So if the norm remains the same, then the first infinitesimal variation of the norm must vanish. Okay? So the infinitesimal variation of the norm must vanish, and that gives us the following. That gives us what? Let's see. So now what we're going to do is to take this quantity and rotate a bit. Okay. So that's going to be delta t. Suppose I rotate it with Tc. Okay. So the change in Ta will be proportional to Tc commutator Ta. Okay. So we're going to get Tc commutator Ta, Tb. Okay. This norm, whatever it is, plus Ta commutator Tc commutator Tb has to be equal to 0. But we know what this quantity is from those relations. That's FCCAM Tm norm Tb, which was dmb. Okay. Plus here we had dam FCBm. Okay. And that whole thing has to be 0. This quantity has to vanish, because the change in the norm after rotation to first order must vanish. And therefore we conclude that if we use this D matrix, whatever it is, okay, to raise indices, okay, so if we use this D matrix, whatever it is, to raise indices, then this, so we'll just use this as a metric to raise indices. So then this becomes FCAB plus FCB A is equal to 0. Okay? So that tells you that this F is antisymmetric under interchange of this new raised index and one of the other indices. First two were automatically antisymmetric. So that tells you that if you take this norm and use that to raise indices of F, then these F's are completely antisymmetric. Okay. Let's keep going. What? What if our group is not connected?
No, I'm saying then we still want the inner product to be invariant under any group
If
action.
it is not connected, then it is in that connected component. Then everything goes to.
Oh, sorry, we're talking about infinitesimal generators at the moment.
So that is in the connected part.
Part,
Yeah,
yeah.
right. Then I'm saying you still want this inner product to be invariant under any group action, not just the infinite.
Not just the infinite part. Okay, it's true. It's true. At the moment, I'm just using though the fact that it's in particular invariant under the connected part. So I'm trying to get it. I'm trying to understand the consequences for algebra.
Okay.
We could have a more global. Yeah. Okay. 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 Now, the next thing that we can argue is the following. Suppose we've got a particular representation. Okay. Now, you know, this matrix D fixes some effective normalization on our space of generators. Meaning we're free to change our normalization in the space of generators, free to take linear combinations. But then D changes as well. So if you freeze on a particular D, you're saying something about the basis elements you're using in your space of generators. Okay? So now the next thing that we want to do is to ask the following question. We want to ask, what can we say about trace TA in some representation R, TB in the same representation. Okay, so our group has many, our algebra, the algebra has many representations. We've chosen a particular representation R, and we're looking at the representation matrices in that representation. We're taking the trace of that, and we want to know what we can say about this. Okay, so let's see. Once again, this thing, this quantity here, is invariant under group action. Why is it invariant under group action? Well, let's just check. How does, under group action, what do we get? This acts with commutator with, this acts with commutator with, well, let's just do it.
We're saying on any representation, not necessarily the adjoint.
Not necessarily the adjoint. Any representation. Okay, so this acts with
Some u, the operator u inverse, and then you get u, the t, u inverse.
no, but what I'm doing is rotating in the group. Okay, I'm looking at the action of, I take two elements of the group, but in some representation. And then I rotate elements on the group. So this representation, this T is in any representation, but the action on the T is always in the adjoint representation.
Yeah.
Okay, so we will, because what we're doing is acting on group elements, which are always acted on by adjoint. Okay, so this will always act on by commutators. Okay, and by using the same basically the same algebra, we'll see it's invariant. Is that sort of clear? Shall I go through it? Is it clear? Yep. So this thing is always invariant, so it has to be proportional to, I mean, now we are assuming, the simple group and so on. Okay, that there's a unique invariant, there's a unique, let's say it's a simple group like SUN, SON. It's got a unique invariant inner product. Okay, of course, if there were two groups, if it was SUM times SUN, you could have chosen the normalization of the inner product in the SUM part and the SUN part separately. Okay, then you would have had more choice. But suppose we're dealing with what people call simple groups, so that everything, there's no path that has that it doesn't break up in a direct product of algebras. Okay, so we can always deal with that case later. Okay, so then it has to be proportional to DAB times some number, and we call that number R, TR. That TR, okay, is something that characterizes the representation. You see, if we change the normalization among group elements, among generators, it changes DAB, but it doesn't change TR. See, because these transform like tensors. So this TR is invariant under changes of basis within the algebra. It's something that characterizes the representation itself. You see, because under a change of basis, this side transforms, this side transforms in exactly the same way. From, for instance, the definition here. Okay, so those things cancel out. So this quantity is some invariant that characterizes just the representation itself. Okay, of course, the value of this can be changed by rescaling these guys, but not the ratio of this to DABC. Is this clear? So there is a number that characterizes representations, okay, which is this quantity in units of DABC once we've made a choice of DAC. This, yeah, okay, fine. I mean, really speaking, we could of course always have rescaled see, this DAC is only unique up to overall normalization. Or up to overall, right, up to basically overall.
Yeah, rescaling.
Rescaling, yeah. Oh.
It's like a Shor's.
Yeah. Yeah, there'll be some convention or some ratios that we will look at as you will see, in which such normalization kind of things will go away. What will be really invariant is the ratio of this T between different representations. That will be just completely invariant. They're completely independent of all conventions. Right, like some sure thing. Okay.
I would say that think even TR would remain fixed, wouldn't it? Because I mean, over there, if we just scale TA with lambda,
Yeah.
will.
Once we've made some abstract choice of DABC,
Yeah.
TR is completely fixed. But there's some choice in what we do with TABC. See, you know, I give you two matrix elements,
Yeah.
and I tell you that the norm is, you know, in my particular normalization, if the two are equal, it's delta AB times 1. This is a group invariant norm. You tell me for the same guys, it's delta AB times 2. There was just that overall scaling in overall norm right at the beginning.
Yeah.
That I'm saying that also was some sort of ambiguity because it was in your hands.
Yeah.
So that overall scaling ambiguity affects this TR, but it affects the TR for all representations in the same way. Okay, and therefore will go away in ratios. We'll see that everything physical will involve things that have no ambiguity at all. Okay, excellent. Yes.
This norm is also in any representation.
What?
This is also in any representation.
No, this norm is on this abstract space of generators. So there's no representation here. You know, so for instance, in SU2, the generators are Jx, Jy, Jz. And this norm is on the space of some linear combination of Jx, Jy, and Jz. You give me a generator and another generator, and I'll give you a number. It's in some abstract space. You understand? There's no representation involved here.
How to calculate those numbers?
You see, all we can do is to ask, is there a inner product structure that remains invariant under group action? Basically, there's a unique such inner product up to overall scaling.
In fact, you can give this, if this is a Lie group
Yes.
with nice compact and so on.
Yes.
You can make it a Riemannian manifold.
You can make it a
Riemannian manifold, and then this will be the metric on the Riemannian manifold. For
Yeah.
example, if you have SU2, this is
Right.
S3,
Right.
and then you can give metric on S3.
And you're saying
S3,
the norm induced in tangent space on that by that metric.
yes, and this is this preferred Riemannian metric, which will be both
Left and right
invariant
Exactly.
of the group action.
Exactly. And it's essentially unique up to overall scaling. Because, you know, as in the particular case of SU2, we've got a sphere, but nobody tells you what size sphere it is. So there's clearly one ambiguity about overall norm. Right? I mean, clearly linear conditions like this cannot fix any overall norm. Okay? Fine. And the last, well, we have 3-4 things to define. Oh, okay, I'm sorry. We have 5-6 things to define. I'm sorry. I'm sorry. The next thing I want to define is the quadratic Cassidy. Okay. So given any representation R, I have TAR, TBR. And now I define this with a DAB. Okay, so now what do I mean by DAB with lowered indices? Well, I just use D is my metric.
Yeah, and once the metric is defined, it's inverse and everything.
It's inverse, and in fact I use it just to lower it. I use D to lower D. Yeah, okay, it's inverse. Sorry, it's inverse, and then that, sorry, you're right. DAB is just the inverse.
Yeah.
DAB is equal to DAB inverse.
Yeah.
Okay? Because of the properties of the inverse, this has exactly the right tensor properties in indices to be completely lower. Because this times this is equal to 1. Okay? And so then what I do is define this quantity here. Now, this quantity is also invariant under choice of, you know, it's a scalar under linear redefinitions of T, because all indices contract. Okay? And this quantity commutes with all TC. Okay? Let's check that. Suppose we have TC commutator TAR, TCR commutator TAR TBR DAB. Exactly, exactly. But let's quickly do it. So this will give us TA, so one term is TCR, commutator TAR times TBR plus TAR into TCR TBR times DAB.
And now this structure also.
Now we use, we'll get FAB, FCB, yeah,
E going to be on the next second one.
and A going to be on the next one. Exactly.
Asymmetric of the contracted with the symmetric.
Exactly. Exactly. So come, let's just finish it. So this is TF, CA, TR, M, TBR plus TAR, TMR, FCBM and DAB.
Yeah, I think probably the lower the index on F.
The second one is to you.
On the second one,
If you do AB flip, then you get this TRM, TRB common.
if I do an AB flip.
In
Very good, very good. Yeah, so BA, excellent, excellent. So I get T, so then this becomes TM, TA times, and this is TATM. And
BC
And then you have the TM and the TA, which you
CN
swap the order.
antisymmetric in BC. Use the antisymmetry of BC.
I use the antisymmetry of BC.
One of them is CB, one of them is
Ah.
BC or not?
I had CB here.
Oh, but now if you take the TA and the TM, and then swap the order of one of those two, and then replace it with the last,
Yeah. Yeah, yeah,
right?
yeah.
You'll get basically a minus between the two, and then
Wait, the M is the guy that, maybe I want to raise this guy here. Just a minute. Maybe what I want to do is either raise or lower everything. Just one. Let me just lower everything. So this will be DCB so DC C prime, DB B prime, TM F C prime B prime M wait, this one was already lowered with an A. This one was already lowered with an A. So let's just do that. Sorry.
yeah. I mean,
Ah.
it is a lowered B really, because that was an A.
What?
On the F, it was originally an A, and it's really a lowered B.
Yeah, sorry. This should be something obvious. I was just wondering.
Both of them lower A or
I mean, it's an anti-commutator of TM and TA, essentially.
both of them are lower AM.
Both of them are lower AM. Exactly. But why is it 0? Just a minute. Oh, maybe this is the trace. I forgot the trace. Trace. Oh no, the whole thing should be without. No.
No, the Cassidy
It's without. It's an operator. Yes. Yeah. Why is it? Just a minute. Sorry. Why is it working? I did this right.
That's when you already swapped the A and the B.
Okay. The A and the
You already swapped those.
A and the B. Okay, fine, but it doesn't matter, right? I choose to lower one of them. Okay. I'm sorry. Give me 1 minute. This should be some obvious thing. F C. Now this is A M T I'm not writing the R, TA, right?
Yeah.
And then this is,
Anti-commutator of TA1 TA.
right, and this is
TA TA.
TATM with F
CAM.
C
Lower AM.
AM.
I think the variation has to be constructed with the trace probably.
Why? The whole operator should be invariant. Just
Yeah.
1 second. Yeah, just 1 second. Just 1 second. And then.
And then does it have to be
This is-
symmetric?
Okay, so it's FCAM.
Is the F anti-symmetric in the A and M?
Yes.
Oh.
Then you have symmetric times the anti-commutator.
Ah, that's it. Thank you. Exactly. So this is FCAM AM times anti-commutator. Anti-commutator. TMTA. Which is equal to 0 because this is anti-symmetric.
Yeah.
Thank you, Yankee. And this is symmetric. Yes. Okay. Great. So this quantity is invariant. And with a given choice of dA, with a given choice of your dA norm, is a number. So this is called QR. Okay. So now we've got two.
That's a number or the trace of that is a number?
No, the whole thing is a number because the whole operator is proportional identity
Identity, right. Sure.
because it's Schu's lemma. Yeah, this times identity. Right? And so this quantity is a number, this quantity is another number. And the product of these two numbers then will also be completely, will have no ambiguity in your normalization of these. Because this, no, maybe the ratio of the two numbers. The ratio of the two numbers.
Ratio of QR by trace of D.
Exactly. Ratio of QR by trace of D. No, I'm saying just this divided by this will also be completely unambiguous. Because if you want, you could take this on that side. So then both of them have a DABC on that side. So the ratio of these two numbers will be completely, it will not care about the size of your S3.
First line, in the first above line, you
Yes.
can multiply with DAB lower on both sides.
Exactly, let's do that.
Then left hand side, and the left hand side is basically dimension of the representation times QR.
Times TR.
Left hand side.
You're multiplying here. No, here. You wanted to do it here, right?
Here you multiply with DAB lower on both sides.
Okay, DMN is lower. This DAB, AB is contracted here.
First line, above line. First
Fine.
line, multiply DAB lower on both sides.
Yes, so you get TR times dimension, I agree.
On the left hand side, you get QR times dimension of the representation. Left hand side.
Ah, the left hand side. Okay, excellent. So,
Trace gives you dimension.
excellent,
and
excellent. So you want to give a relationship between these two numbers.
Yes.
Okay, excellent. Let's do what Indranil said. So we take the left hand side and we multiply by DAB. So DAB. So as Indranil says, what we get is that the left hand side is DAB
A dimension of the representation on the left.
QR
Times dimension.
times dimension of representation. Let's call that DR. QR times DR is equal to
TR times
D group. Dimension of the group
dimension of the group, right? Sorry.
times TR. Excellent. And therefore that gives us the following ratio, that QR divided by TR is equal to DG divided by DR. Absolutely. So that's very nice. And note in particular, this ratio is completely physical. It's given in terms of invariant data. It has no ambiguities like the size of the sphere, as we could have seen from here. Because this thing could have gone there, and then both of these have the same, this TR and QR have the same rescaling ambiguity under the rescaling of the norm DAB. Okay, excellent. Excellent. So we've got two invariants, this TR, this QR, and as Indranil pointed out, they're not independent. They're simply related once we know simple things. Okay. Now the next thing I need to do is to remind you about roots and weights of this Lie algebra. Okay. So as you remember, what we do is to arbitrarily choose, given the space of all TAs, arbitrarily take a maximal set of commuting maximal set of commuting T's. Okay, that maximal set of commuting T's we call HMs. Let's see if he uses M. HIs. Okay, and these guys are called the weights of the algebra. Or the Cartan subalgebra. This is what's called the Cartan subalgebra. Sorry. Okay. For instance, for SU2, the Cartan subalgebra would be just J3, because the maximal commuting set is just one object. But if we had, let's say, SO6, the Cartan subalgebra could be chosen to be rotations in the 1-2 plane, rotations in the 3-4 plane, and rotations in the 5-6 plane. Clearly these commute with each other because 1-2 rotations have nothing to do with 3-4 rotations. And you can easily convince yourself that this is actually the maximal set. So the Cartan subalgebra would be 3-dimensional for SO6. Okay, for SUN it's n-1 dimensional. Again, you can easily check all this. Okay, so so you choose some convenient basis of maximally commuting elements of this of your algebra, and then you take the rest of your algebra and ask for look at the commutation relations between HI and everything else. Okay, so when I've got an element such that now I'm going to think of this like an eigenvalue equation. HI acting on E's, okay, HI acting on E's is going to give me some linear combination of other E's, and then I diagonalize that action. Okay, so I've got some vector space, the space of all the generators that are not part of the Cartan algebra. You can take it to be the whole thing if you like, but the HIs with the other H's give you 0. Okay, so basically what I'm taking is the adjoint representation itself. Okay, I'm taking some of the elements in the adjoint representation, the maximally commuting guys, because they're maximally commuting, they can be within the adjoint representation they can be simultaneously diagonalized. Okay, and I'm going to choose the eigenvectors under which this is diagonal. Okay, so the guy, if I got some element such that its eigenvalue under HI gives alpha I, I'm going to label that guy by E alpha. Okay, so these alpha I's are vectors with let's say that the number of Cartan elements is called the rank. Let's not say R, let's say A for rank, second letter of rank. Okay, let's suppose the rank of this thing is A. Okay, so this alpha here is a vector, column vector, which has elements alpha 1, alpha 2, alpha A, giving the eigenvalues of that particular generator under H1, H2, H3, where the action is with commutation. Okay, and I need to check whether you've put in, whether he wants to put an I or not. Yeah, no I.
Because they commute, that's a neutral eigenbasis.
What? Because they commute, you can simultaneously diagonalize. Okay, excellent. So now this is great. So this way we find once you pick a choice of maximally commuting, basis for the space of maximally commuting elements, this way gives you sort of distinguished basis for your Lie algebra. There's some ambiguity in what your HIs are, but once you fix that, This gives you a preferred basis in the set of generators of the Lie algebra. Now the next question you ask is, what is E alpha E beta? And does he put his alphas up? He puts his alphas up, so just a minute. The next question you ask is, what is E alpha E beta? Okay, now the one thing is totally obvious. You see, this guy was a vector of charge alpha I under Hi. Sorry, this guy was a vector of charge alpha I under Hi. This guy was a vector of charge beta I under Hi. So the total is a vector of charge alpha I plus beta I under Hi. The charges just add, as you can check with the commutation of Hi with a commutator or with a product rule. Okay? So this quantity has to be, if it's non-zero, it has to be proportional to E alpha plus beta. Okay? Now we have two cases. Either alpha plus beta happens. Okay, this vector, you see, we've got all these generators which we diagonalized under the action of the Kaplan subalgebra, and their eigenvalues we call roots. Okay, so the various possible sets of these alpha 1, alpha 2, alpha 3, these are vectors in this A-dimensional space. And how many such roots are there? Well, how many non-trivial? There are, of course, yeah, the dimensionality of each root is A-dimensional, yeah. That's number of cartons. But the total number of each roots, the total number of non-trivial such roots, is the dimension of the group minus the dimension of the carton. Is this clear? Okay. Now, if alpha is some root and beta is some root, you have two possibilities. If alpha plus beta is not a root, then of course you're just going to get 0. Because whatever it is has to be some element of the Lie algebra, has to be some element with charge alpha plus beta. If no such exists, the only option is 0. Okay? So if alpha plus beta is a root, okay, then you'll get some number, I mean generically you'll get some number times alpha plus beta. Okay. Now, note also, you could get 0, only you won't, because the Jacobi identity will completely determine all these numbers. But we'll see. At the moment we're leaving it some number which at the moment might be 0.
No, I'm saying that you can have alpha plus beta is 0.
Ah, you can have alpha. 0 is also an allowed value. Okay, yeah, so suppose we have E alpha and E minus alpha.
Then it's a
Charge 0 operators and a lot of them.
Which is, then it has to be some linear combination
of the carton.
of these cartan elements zeta I Hi.
If you use Jacobi identity.
Exactly. Now the Jacobi identity basically
Jacobi identity to say the first line. The charge adds up is a statement of Jacobi identity.
Charge adds up is just a statement of commutation of Hi with this.
Which will be, after using Jacobi identity, will be the sum. Because every time you will have H acting with E after using Jacobi identity, and that will give you a number times that.
But even without Jacobi identity, it's just, I mean, suppose we open this out. This is E alpha E beta plus E beta E alpha. Minus Hi. Hi commutator this. Now I just use the commutator formula. This is E alpha Hi commutator E beta plus
First one, you're saying both of them has charge alpha plus.
both of them have charge. I'm just saying that charges add. It's a trivial statement. You don't need to use anything.
Then what does
Jacobi identity will help fix these normalizations. So far we've not said anything about what these numbers are. Okay, but I'm claiming that okay, I'll tell you exactly what the Jacobi identity. The Jacobi identity tells you that the normalization, that the number with the guy with is 2 alpha dot h divided by alpha square. And at the moment we are not saying anything about this. Epsilon of alpha beta. The second line we get by Jacobi identity. Now let's see how that works. Just 1 minute. With the above line, we've not said anything. Yeah, we will use something. Just 1 minute. These, yeah. The use of Jacobi identity tells you that these numbers have to be plus minus 1. That's what Wilczynski tells us. But just 1 minute, Firstly, first I wanted to argue that if E alpha is a root, E minus alpha must also be a root. Okay, and I think the argument for that is just taking the argument for that is just now. Do I know that HI's are Hermitian? That's the question. I want to take a dagger of this equation.
You can make the constraint that you only look at those kind of representations, right? Oh no, H is in the algebra.
Yeah.
So H,
Yeah, we
H is
know.
the diagonal subgroup.
We-
So
we-
H has to be Hermitian.
We know because the adjoint representation is defined by FABC.
Yeah.
Okay, and we know the properties of FABC. Okay, so the question that we are asking is FABC now, okay, we've assumed that F's are all real. The F's are all real and they are antisymmetric.
You need them only to be antisymmetric in the last two indices for the thing you want to make. And then you say there's an I in front, so when you take the dagger, you get back to yourself.
Yeah, now what about this DABC? Can I always diagonal? I think I can always diagonalize. Yes. Yes. Okay, I'm not going to try to prove this, but you can always choose a basis such that DABC, DAB is some
Delta
number
AB.
times delta AB.
Yeah, that's. I mean, it's usually half times delta.
Yes. For this purpose, I'm not going to choose yet a normalization. In this case, these F's are clearly a Hermitian representation.
Yeah.
Why did you need this to make that statement?
Because F.
Oh, you want to drop the, okay.
I want.
You want to lower the B so you can get the emphasis.
Exactly.
Right.
So, because this now is an antisymmetric matrix, and there was an I in the representation, the action of F. Oh, anyway, antisymmetric, symmetric, basically the same thing. I mean, what I mean is, if you want to say that it's Hermitian, you put an I. Okay, so we've seen that then therefore the adjoint representation is a Hermitian representation. Okay, a representation in which all the operators are represented by Hermitian operators. So the H's are by themselves Hermitian, E's may not be, but you know, suppose I take the Hermitian conjugate of this equation. On this side, what I get is exactly, I get E dagger alpha commutator HI is equal to alpha I E alpha dagger. And then by switching the signs, I get a minus sign. So then I've shown that if you have an E with root alpha, there is a corresponding E with roots minus alpha.
That is the dagger.
And that is in fact the dagger of it. It's like J plus and J minus in SU2. You know, J plus had J3 value 1, J minus, which is its dagger, has J3 value minus 1. Okay, so this business is not academic, because every time there's an alpha, there's also a minus alpha. So this is a very important, element. Okay, and the last thing is, how are we going to actually use Jacobi identities to fix this?
That will also show if the right hand side can't be other than alpha by beta in the first one.
That it can't be alpha other than alpha plus beta is totally obvious.
Yes, charge conservation told you.
Yes.
Sorry.
Yeah.
Will also push you.
Okay, Jacobi identity may also push. Okay, excellent. Now let's just see roughly what Jacobi identity.
Actually, I'm a little
Go on.
by this. I mean, about this general epsilon alpha beta. I mean, if let's say we took and just artificially replaced the E's with AHs, then that should go to 0 in some limit. And if
Why should it go to 0?
no, I mean, because we have
If you replace-
if we replace the E's with H's, I mean, I was just thinking, I mean, maybe that's too artificial and
No, yeah.
if that does not exist.
No. I mean, so we've got various different cases. These are E's such that alpha is not equal to beta.
Okay.
These are E's such that alpha and minus alpha.
Yeah.
And H's are not allowed in this.
Yeah,
in
so
this set.
that's what I was wondering. And the restriction is that, I mean, it's alpha is not equals beta and neither is equal to 0.
H, yes.
Neither is
Yeah.
equal to 0.
So the term root is really used for the non-zero eigenvalues.
Yeah.
Okay, these are results for those
So
roots.
I was thinking of having some general formula.
Yeah, no, we've sort of broken all that symmetry. You know, for instance, in this notation, that's completely broken.
Yeah.
Okay, and okay, which kind of Jacobi identity will be
So
used?
when you take HI commutator of the first line, E alpha, E beta, that's right.
HI commutator of the first line will just give me, oh, but you want to use Jacobi identity. Okay.
For both of them, you will get E alpha plus beta once you use it.
I mean, so what will I get? Once I'll get HI with this, and once I'll get HI with this.
So when you get HI with alpha, you get some number times E alpha.
Yeah, you're trying to argue that only E alpha plus beta can appear?
No,
Or you want the number?
Number.
Number,
Both
let's-
of them will-
Okay, let's try what Indranil is saying. Okay, suppose I use HI with the first guy. So I get HI commutator E alpha E beta. Okay, now we know that this plus E alpha commutator E beta HI plus, and move one more back, E beta commutator HI E alpha, okay, is equal to 0. Okay, but these we can just replace as Indranil wanted. So this is minus E alpha E beta with an alpha I, with a beta I, thank you, beta I plus alpha I E beta E alpha.
Then move to the other side, switch the beta and alpha and any of them on the second
we're just getting that the sum of
You're just getting that it's an eigenvalue.
that it's an eigenvalue.
What about the eigenvalue? Let's use this equation.
This equation is not going to tell us anything, right? Because it's just telling us that if we assume that now from here, this is whatever normalization, okay, the normalization is going to cancel out on all three sides.
Yeah.
Because everywhere we have E alpha, E beta. Yeah. Okay.
Just charge is
It's just the same thing, the charges. Yeah. There will be other. Maybe we should obsess on this. Okay, but let's try one non-trivial and then we go on. Let's try. What about HI's
No, I was going to say, you
with
say that every relation is
this? That will give you no information. Sorry.
You say every unitary every relation is a rotation and a scaling, and you know that from the E alpha betas, right? So it has to be a rotation of one into the other. What we had over there going on of H going on E alpha and a product E beta, right?
You
So the scaling is going to come from the eigenvalue, and then the other thing, it just has to be a rotation.
okay?
Unitary.
Yeah. You know, I think if we take HI commutator with this,
Yeah.
it's trivial, and HI commutator with this is also trivial. Because HI commutator with this will just tell us that this whole thing has zero charge,
Yeah.
and this thing does have zero charge. So we'll not give you any new, information. Okay. However, if we take E gamma commutator with this,
Yeah.
and E gamma commutator with this, especially with this, let's try here. E gamma commutator with this will give us some information. Let's try that. Okay, we take E gamma commutator E alpha, E minus alpha. Okay, is equal to E gamma commutator. At the moment, I won't tell you what it is. This was zeta dot h. Zeta alpha dot h. Okay, now this right hand side is minus alpha. This is, let's say, zeta a h a. So alpha a, gamma a zeta alpha a. Okay, times E gamma.
Times E.
Gamma.
Yeah.
Okay. On the other hand, this guy, now I'm going to use Jacobi identity. Okay. But what am I going to get? I'll get
Oh, from there, the epsilon.
You get your relation between epsilon.
okay.
And alpha, epsilon, gamma.
Okay. I'm sorry. I'm not going to try to work it out now. If you want, I can think about it and come and tell you next time, or you can go and look it up. The claim is that the Jacobi identities completely fix this. I'll just check that that's properly the claim. Yeah, the claim is that Jacobi, if you take all Jacobi identities with each other, this form is completely fixed where this epsilon has to be plus or minus 1. Now, what?
One of them you fixed, the lower one probably. How did the lower one appear to be this alpha dot h?
Yeah, that is some very simple thing, right?
But is this, I think with some sort of a, because there could be different bases, even with this identification or diagonalization. This is some sort of a subunity basis or something, but
Wha-
there are inequivalent bases.
What do you mean?
You are asking for the diagonal basis with respect to Cartans.
Correct.
With this condition, probably there are inequivalent famous bases.
Yeah, but with whatever basis you choose, you'll get the same answer. I mean, the bases may give you different values of alpha, for instance. But this is supposed to be universal. Okay, give me 1 minute. Let me try to argue this. Just, let me give you an argument from this. I'll just check that this is the claim. Oh. Oh, wait. Maybe it's this easy. Wait. Suppose I do this. Suppose I take a trace, just 1 second. Just 1 second. Okay, no, I don't. Okay, give me 1 minute more. Let's see if I can think of something. What Jacobi identity is this? Maybe I want to do this. Suppose I take hi e alpha is equal to alpha e alpha, and now suppose I do this with an e minus alpha. Suppose I try this. Okay.
Why is it different than using hi on this e alpha e minus alpha after using Jacobi identity? Why is it different than that?
You're saying this will just give us the weights are the same. Maybe.
I think at some point the trace has to be like,
Yeah.
If we take hi commutator in the first line,
Yes.
then it will give epsilon is equal to, it will give alpha plus beta commutator of e alpha comma e beta is equal to epsilon.
I thought it just cancelled out.
that is
It just gave you no condition on epsilon. Yeah. Just 1 minute.
normalization of h might be
Let me just see what this gives. I'm not going to use Jacobi identity here, so that's minus hi, minus hi commutator yeah, you're right. It just gives the same thing. Sorry, I don't know what fixes it so easily.
I think probably the trace normalization has to come here somehow.
Well, the trace normalization seems to be cancelling, right? The D cancels, you're taking two dot products, alpha dot alpha and alpha dot h.
No, the overall normalization cancels, but I think the fact that we have to use the inner, I mean, what I mean is we have to use the inner product.
The inner product has to come somewhere.
Yeah. I mean, the trace, no, I mean, the overall normalization has to.
Good point.
But I mean, this can only come from an inner product.
Good point. So what you're saying is, what about taking this and doing trace with h?
Yeah.
Good point. Let's see. And then, oh, this might work. Let's try exactly what you were saying. Okay, let's try. Wait. Suppose we have e alpha e minus alpha is equal to zeta I h I. Now, one new suggestion is let's take hj and take trace. And we take trace. Okay, so now Upmanyu's suggestion is that now we use Jacobi identity
inside that trace.
inside here.
Yeah.
So here we get
Commutator that you have taken initially. What is the quantity inside this?
the quantity inside the trace is E alpha, E minus alpha
With respect to
with 8j.
it's multiplication or commutator?
Just multiplication, otherwise we'd get something trivial here.
Yeah. Otherwise, the left hand side is 0.
Yeah, but now I'm going to try to use basically lots of cyclicity. Let's just work. This we can rewrite as what? So this is trace of hj E alpha E minus alpha minus trace hj E minus alpha E alpha. Okay, and then I use cyclicity.
Yeah, cyclicity, and then rewrite it as some commutator of
Yeah.
Hj and
So then I can make it commutator of E alpha hj. That's equal to minus
yeah.
trace hj E alpha E minus alpha. Which will give me minus trace, won't work,
yeah.
alpha I times E alpha E minus alpha.
Yeah, and you have to fix some condition on that. You have to say what it is.
But I'll tell you what.
If you take the equality up there, right?
Yeah.
And the EI, HI, HJ, that'll just
Yeah.
give you EI delta IJ, right? And then you're getting that the trace of the two things that you're looking for, which will just give you the overall scale, is going to be essentially alpha I.
Yeah, you have to decide one particular.
Yeah, you have to say that this thing is independent of alpha, if you want. If you want that this thing. No, you're right. It tells you that it's proportional to alpha I.
Yeah.
If you know that hi. Okay, sorry, it's just not worth wasting wasting the time here. I'll clear this up. Okay, I'll come and tell you next time how you get this. Let's accept it for now. It's supposed to be some simple use of Jacobi identity. I can't see it at the moment, but okay. Okay, let's move on. So let's just review what we've got, and then move on to what we really wanted to discuss, namely which was current algebra. Okay, so let's put one or two definitions on the board. So I'll just put a few definitions. There was TA TB was equal to I FABC TC. There was TATB was equal to DAB. We had DAB was equal to DAB inverse. Then we had that we used this to raise. FABC was completely antisymmetric. Then we had that the quadratic, we had two things, right? There was first the trace TAT in some representation R BR is equal to DAB times TR, and we had DAB times TATB is equal to QR times DAB, no, just QR. And then we had Indranese identity, which was, can somebody remind me, QR divided by TR? DG divided by TR. Okay, excellent. And of course we had this relationship that HI commutator E alpha was alpha I E alpha, E alpha E minus alpha was equal to 2 alpha dot H divided by alpha square, and E alpha E beta is equal to epsilon alpha beta E alpha plus beta, where these were plus minus 1 apparently. Okay, now let's keep going. What we want to do is to study conformal field theory, and we want to study the most general algebra that you can generate by holomorphic spin 1 currents. Okay? Holomorphic spin 1 currents, because these things close in a nice way, as you will see. So consider we've got some JAs. We take the set of all holomorphic spin 1 currents. By spin 1 I just mean h equals 1, h bar equals 0. Okay? I take the space of all 1 comma 0 operators. You remember we proved sometime last semester that if an operator is 1 comma 0, it is necessarily independent of z bar.
It has dimension 1, right?
It has left dimension 1, right dimension 0. Yes. Okay. Now what I'm going to do is to ask, what is the current, suppose I take the OP of, so let the full set of such operators be labeled by this label A. And then what I'm interested in is, I've got JB of 0. What can I get in the operator product expansion? Good. So the left hand side is a dimension, dimension 2 object. So we could have some DAB by Z squared. Let's call this D tilde AB at the moment. Okay, and we could have some F tilde ABC JC by Z. And there's nothing else singular that we could have in the algebra. And just like when we had t with t, the most singular term was 1 by t to the 4. Then there could have been a 1 by t cubed term, we argued. There couldn't have been in that case because antisymmetry. Then there was a 1 by t squared term and a 1 by t term. 1 by z squared term is 1 by z term. So this is the same thing. It's just a much easier algebra because we start with something of dimension 1 rather than dimension 2.
How these are fixed?
We don't know yet. There's some numbers. What these numbers are, we don't yet know. These are like the analogues of the central charge.
Oh, we are just calling it.
We just some names. No, that we will argue. That's why I put the tilde at the moment. Okay. Now, once we have such an operator product algebra, okay, we can play the usual games. Okay, so if we've got this JA of Z, we can expand it as sum m is equal to minus infinity to infinity JA divided Z m plus 1. Okay, the usual thing, the game we've got very used to. And then we can use this OPE to compute the commutation relations between JAM and JBN. Okay, so let's do that exercise. Suppose I was interested in JAM JBN. I was interested in this commutator. Well, we know that it is the charge generated by the current that appears as the residue in the OPE between JA and JB. But the OPE between JA and JB has this. So we get integral. Okay, so now firstly we should, so let's do it more carefully. This guy was what? This guy was what?
That thing that you're pointing out right now.
Huh?
Is it at Z0 then?
No, these are the operators. These are the modes.
Oh, okay.
Yeah, so let's write them in terms of contour integrals. Okay, so this is Z to the M JA Z to the M JA of Z and W to the power N JB of W. And then it's the commutator between these two quantities with all the 2 pi i's and so on. I'm not writing that. Right here I've just replaced. There's some dz by 2 pi I dw by 2 pi I. And then we play the usual tricks. We take one contour around the other and then integrate the result all over. So when we take one contour around the other, we get what? We get the OP of JA with JB. Okay, but what do we get from that?
There will be conic result of delta m plus n minus and 1.
Exactly. So we get dz by 2 pi I, w to the power m, z to the power m, dw by 2 pi I, z to the power n, and then we get dab, d tilde ab, divided by z minus w,
That's the central
the whole thing square. Hang on, we'll see. Okay, plus f tilde abc jc by z minus w. Then we do the contour integral of z around w.
Yeah.
You know, we do the usual thing. We do this contour integral and then integrate around w. When we do this thing, we need to pick up the pole.
Yeah.
So we have to Taylor expand this.
Yeah.
So we get a factor, we get m. So what we get is m, and then what's left is just identity.
Yes.
So we get JAM JBN is equal to m
Time with d upper ab, d tilde upper ab.
w to the power n. W to the power n, and then the integral over w will vanish unless m plus n was 0. Because we need in the end a 1 over w.
No. Unless, I'm sorry, m plus n equals 0 or?
0. Because you see, when we differentiate, this becomes m minus 1.
Okay. Yeah.
Then you substitute w. So the whole thing is w to the power m plus n minus 1.
Yeah.
So unless m plus n was 0,
Yeah.
we would not pick up a pole. Because this guy's a constant.
No, m plus n plus 1 has to, it has to be, but because otherwise z minus w square is downstairs. I mean, it has to be the coefficient of 1 over z minus w.
Well, we already got that coefficient. We differentiated here to get that coefficient.
Okay.
Now we have to do the integral over w. The integral over w has a power of w because we differentiated and then said z equals w. The differentiation made this power z minus w rather than the z.
Okay, yeah.
Okay?
No.
Now what was left was w to the power m minus 1 plus n.
Yeah.
Now we have to do that integral dw. That is non-zero only if m plus n is equal to 0. Because that's the only case in which you have a pole.
Yes.
Okay, so you have m delta m plus n and then d tilde ab.
Delta m plus n 0.
M plus n 0. Here we don't have to differentiate at all because there's just the simple pole.
Yeah.
Okay, so here this just adds up. So we get plus f tilde abc jc m plus n.
Delta. Oh, right, yeah.
And I'm sorry, but Pulchinski put an I here. So I'm going to put an I here all through. So we get this plus I, that I suppose the same I that appeared in the Lie algebra. Okay? Great. So what we've got here, you see, is a beautiful algebra that is an extension of Lie algebra. Why is it an extension of Lie algebra? It's an extension of Lie algebra because if you set both m and n equal to 0, then this term vanishes.
No, that term does not have.
It does because m is 0.
Oh, okay. Alright, sorry.
Okay?
Yeah.
This term vanishes,
Yeah.
this term doesn't, but it's exactly the commutation relation we started out with in defining a Lie algebra.
And
Yeah.
the, for m
The 0, 0.
for m equal to n, that term has to vanish because this multiplies a symmetric tensor. Because when I said a equal to b and m equal to n,
Oh, sorry, say again, for m equals,
say m equal to n
m is equal to n.
and a equal to b, the left hand side is identically 0.
Ah,
So right hand side, the quantity that multiplies a symmetric structure in AB.
yeah. You're saying A, in particular set A
Yeah.
is equal to B.
So right hand side has two tensor structures in AB space.
Yes.
One is symmetric, one is antisymmetric. Symmetric one is DAB.
Yes.
Why is
So-
the AB symmetric?
Yeah,
Well, this is anyway 0, right? You're setting m equals n and m is not equal to 0.
Most singular part.
I'm giving an argument.
Because when
Huh?
you swap the two,
Yes.
the minus and then
In
end up
terms of AB,
Uh-huh.
if you write the right hand side,
Huh?
you can write symmetric part and antisymmetric part. And the coefficient that multiplies the symmetric part has to vanish when m is set to
Oh, when m is equal to
n equal to 0.
when this, I'm saying,
uh-huh.
suppose you have two parts, one is symmetric, one is antisymmetric
Mm.
part. Then the part that is symmetric
Hmm.
in AB,
Hmm. Hmm. Hmm.
that part,
Hmm.
if you set m equal to n,
Hmm.
and
You're
a
giving
equal
an
to-
argument that this had to be 0 when m was n.
Yes, when that is the argument I'm giving, because it is symmetric otherwise.
Yeah, because it couldn't have been. Yeah, you're saying if I choose A is equal, right, I just choose m equals n, then it's symmetric in AB, the anti-symmetric in AB. This term is symmetric in AB, so the coefficient then had better vanish. And it does vanish. It vanishes when.
More
That
generally,
does not completely determine the structure of the coefficient before it. It could have been m squared, m cubed.
well, it could have been any
Yeah.
function that's
It could have been. I think Indranil is just saying that something is
Yeah,
consistent.
That structure is determined.
He's just saying that something's consistent. That he was just doing a first order check. Some symmetry at the right hand side should not be violated on the left hand side. And by the way, he's also basically arguing that this f tilde looks like it should be anti-symmetric. Because if m was equal to n,
Yeah.
this was anti-symmetric, so this had better be anti-symmetric.
Yeah.
But of course, but this is the same thing. You see, now, but for a moment, just focus on m is equal to n is equal to 0. This is a closed subalgebra because 0 with 0 gives 0. So of this huge algebra, there is a closed subalgebra. And that closed subalgebra is exactly what we started looking at to define a Lie algebra. So we see that the 0 part is a Lie algebra.
Yes.
Okay? Now we're going to assume that our Lie algebra is compact. Compact, simple, blah, blah, blah. It's like the kind not a direct sum of things that commute with each other. Okay? And we can later deal with the more complicated part. It's basically a direct sum of these things. Okay? So already we found that this structure is a beautiful generalization, an infinite dimensional generalization of the commutation relations of a Lie algebra. And in particular, it contains the Lie algebra as a subalgebra. Okay. Now, notice that this immediately allows us to identify, this is one of the questions you had, this f. It immediately identifies us to allow this f with the structure constants of Lie algebra, because that was the defining character.
Do we have a constraint that that index has to be finite?
No, I suppose there's no a priori constraint, but we will usually deal with, at least in every case that we will look at it, it will always be finite. You may, like for the space of, I will never look at it for something that's not finite. Okay. Now, let us look at the Jacobi identity between J1, J0 and J minus 1. So now this is some algebra, and the algebra obeys the Jacobi identity. Okay? Because the Jacobi identity is just some trivial statement about matrices. So let us look at the Jacobi identity between, what was it, J1a, J0b and J minus 1c. Sorry, JA1, JB0, JC minus 1. Okay? So what I want is, let's say, this plus J0b commutator, J minus 1c, JA1 plus J minus 1c commutator J1a, J0b is equal to 0. This must be true. I'm going to use this to extract some information. Okay, so let's look at this quantity, J0 with J minus 1. Because m is not equal to n, this term is 0. Okay? So I just pick up this if term. So this term is equal to if bc d j d minus 1. And then I have J1a, anti-commutator of that.
There will be central term from this one.
There will be a central term from this one, exactly.
And the last one as well, by similar logic, but
Exactly.
they might potentially cancel a more.
No, what we're going to show, what we're going to see is that this d
Yeah.
will have to raise the f's. We're going to see that this d tilde is going to be proportional to the invariant inner product matrix, the metric matrix. That's what we're trying to prove with this manipulation. Okay, so we've got an I, let's put it outside here. Okay, let's complete this. So here we've got a term which involves this d, which is dAd times FBCD and J1, J minus 1. So FADM, and then we get J0, J0M. Oh, sorry, I mixed it up. I mixed it up. This term was this piece with an extra I, so minus this, and then there was this with this, which was just plus I, J1 with J minus 1, D, A, D. So F, B, C, A. Okay, D, D tilde, DA. Right, and did I get the plus 1 minus 1 right? This should have been J
Yeah,
plus
it's
1.
plus
I got that right. Okay, so this guy was these two terms. Okay, I'm going to work out each of these terms. So now let's look at this guy. This guy was JC, J minus 1, J1.
Yeah, the central term wouldn't eventually contribute because there's another commutator taken with J0. So the central term will go away there.
Exactly. Exactly. We get a constant, but because there's a commutator,
Yeah.
that goes away. So all we get is F, I, F, C, A, M, J0, J0, M, and then the commutator of J0B, J0M. Okay, so this then gives us minus FBM Q J0Q. Right? And the third term gives us J1 with J0.
In should be the free.
No, M is contracted here. Q is the free.
Okay. I think only Q is also contracted
With the J0.
J.
Yeah, okay. What's the structure going to be? We're going to get
Only
three.
ABC are free indices.
Right. We're going to get three terms here. These three terms, or each of them will have a term like this J0. The thing that multiplies this J0 will be the Jacobi identity for Fs. You can see that each of them is going to be a product of two Fs, right? Here there will be a term which will give us J1 J0 is equal to some is equal to some J1. And then J1 with J minus 1 will give us another J1 J minus 1 is equal to J0. Both coming with Fs. Okay? Those terms are going to vanish among themselves, because that algebra is exactly the same as the algebra had they all been J0s. Do you see what I mean? Suppose I had chosen 0, 0, 0. I would have got all the same things with the Fs. So I'm not going to keep track of the terms with two Fs, because that's guaranteed to cancel. That's the same algebra we did for deriving Jacobi identity for Fs. The new things are the things involving the Ds. Okay? One term we got here was this. Let's look at the other term just involving the Ds. Okay, so this thing here was F A B M J M 1. Okay? Then I. And then this thing gives us with a minus I, because it's J minus 1.
Yeah.
It will give us minus I d Cm.
Yeah.
Minus I d Cm. Okay? And so it's this plus I F B C D. This is d tilde. D tilde dA was equal to 0. Okay. Now what we've got is this. You see, this here the index in F was A, the index that was not one of the raised indices. Whereas here the raised index was A. And what about the minus signs?
No, that's D, right?
What?
That's BCD lowered.
BCD lowered. Yes. So what we're saying is that if we use d tilde to raise indices, if we use d tilde to raise indices, then this A and this C is equal to 0. Okay. Now, have we got this right?
Yes, AB flips.
AB flips, so the minus sign goes away, and then it tells you that it's that the symmetric part between this and that is 0. So what we've concluded here is that this d tilde that appears in the central term has to be proportional to the norm matrix, to the inner product matrix. Has to be proportional to the inner product structure of the D algebra. Okay? So now what we've done is to identify both these things in terms of structures that appear in the Lie algebra. So okay, so we'll choose our normalization of J's so that the term here is precisely FABC for the Lie algebra. Okay, so we choose, that's basically normalizing J0. But then we have no control over the normalization of this D tilde. Okay, so if we choose some standard normalization DAB, we'll worry about what that is in a moment. Then we've got J0A, we've got JA of Z, JB of 0 goes like K hat times DAB, K hat times DAB plus FABC JC of 0 divided by z and this by z square. Okay. So apart from this number k hat, we have completely identified everything. We allowed structure for our OP algebra. It's completely fixed just in terms of the data for a Lie algebra. There's one normalization that we're still to determine. Is this clear?
Just out of curiosity, so what is this k hat called?
It's called the level.
But DAB, suppose I looked at these J's and I said, okay, I know which Lie algebra this is, right? Then DAB is still an arbitrary choice even in the Lie algebra.
Even in the Lie algebra. But you make your favorite choice.
Okay, so you're saying suppose I have a convention with my Lie algebra, now I want to...
Now you, yeah. It's true that at the moment, this k hat has no meaning unless I tell you what. Give you some additional information about this.
Right.
This DAB.
So just starting with the J's, if I were to just start with the J's, there's no real...
Yeah, it's true. At the moment, unless I give you some convention about what this DAB is, k hat is meaningless. Really, but the whole thing here together has meaning. Okay, as we will now see. We will now determine J as this k hat, or we will determine part of it that is physical. Okay, and the way.
If one says that crazy to say that this J, A, J, B, this OP that you have,
Yes.
this AB are some group indices, some internal indices,
Yes.
but J's has some dimension, arbitrary dimension, not spin one.
Okay.
And then one tries to generalize this algebra.
Yeah.
You will get some commutation relation above.
You get some structure. Yes.
Now let me from above structure. Suppose you want to write some symmetric part, some antisymmetric part. Symmetric part I call DAB.
Yeah.
Antisymmetric is FABC.
Yes.
These are my definition. Some symmetric, some antisymmetric. It has to be.
But you might have more than, you might get more than just. See, the thing is that these things close among themselves. See, it was sort of important that the following was true. Because we started with spin 1, the most non-trivial singularity
Was Z square 1 by.
was 1 by z squared, but that had to be constant because whatever multiplied it was dimension 0. So the coefficient of that had to be constant. The first non-trivial, the first singularity that could have a non-trivial operator multiplying it was 1 by z, and that operator itself had to be a spin 1 current. So from dimensional analysis. Therefore, for that reason, spin 1 is very special because whatever you can write down closes among itself. If you choose some spin 4, let's say, you could have singularities, you could have, let's say, a 1 by z singularity. The thing that could come on top of that is some spin 3 operator. And then it's not clear what to do. It's not, that could be some new current associated with some spin 3 operator. Could be bilinears of whatever. It's not clear that you'll get an algebra that closes among itself if you start with spin 4.
But this is exactly the sort of point. In higher dimensions, if you have any higher spin, then you have all the spins.
Yes.
In 2 dimensions, presumably that is not true or something. I don't know.
Well,
So if you can try to do this OP kind of argument,
yeah,
and if you try to write down an algebra,
yeah,
what algebra is this? Some sort of an higher spin algebra that you
yeah.
get?
You get various kinds of, one of the simplest kind of generalizations that you probably know all about is this W infinity algebra. Okay, this W infinity algebra is the algebra of particular currents that appear, let's say, in a free scalar field theory. These currents come with all spins, and then when you take something with all spins, it sort of closes. You can do.
These structures someone cannot write down. That is the most general thing that you can write down, right? The kind of analysis you did is just dimensional analysis and nothing more sort of.
Yes, it's true. Basically I did dimensional analysis and nothing more. But the problem is really this, that if you take spin 4 with spin form, you will also in general get, let's say, 1 by z times spin 7. So you will need to include spin 7 into your algebra. Then you will take spin 7 with spin 7 and you will get spin 15, and this will go on forever.
Yes, this is sort of thing expected also.
Right. So in general, unless something very special happens, you will get an algebra with particles of all spin. Yeah, so something, and this W infinity is of that sort. Okay, so however, there is something very special about spin 1, that the algebra closes just including spin 1.
Yes.
So it's a tighter, nicer structure.
Spin 2 also the stress tensor.
Yeah, spin 2, the stress tensor also closed for the particular case of the stress tensor. If you allowed 2 spin 2 fields, do you remember what was very important was that when you took stress tensor with stress tensor, the 1 by z cube term was 0.
Yes.
Okay, it's because, if you remember why that was, it was because the left hand side was symmetric.
Yes.
And 1 by z cube was anti-symmetric, and that forced it to be 0. But suppose you have 2 spin 2 fields, T1 and T2. Then the left hand side has no particular symmetry properties.
Yes.
Then you would allow a spin 3. And then you allow everything. So, you know, it was very special that you had a single spin 2 field. And, you know, it was special that it was a stress tensor, and then it closed. But if you look at the most general algebra of spin 2 fields, that will also in general go off to infinity.
Yes, we could have written down something like spin 3 by z.
Exactly, a spin 3 by z, you would need two spin 2 fields for that.
Yes.
And then once you include spin 3, you'll need spin 5, and it will just go on forever. Yeah, so it's true that the stress tensor itself, the Virasoro algebra was special, and that, you know, the speciality lay in the fact that there was a clear geometrical meaning for that.
Exactly.
It was basically diffeomorphisms with enhanced by this while business. Okay, so we knew that something like this should work. Okay, here we're trying a more adventurous analysis. We don't start off with some geometrical notion of what should appear. We're just taking the most general algebra of spin 1 fields and finds that the structure closes among itself, and we're forced into the structure of Lie algebras. It's more somehow
More special.
yeah, more special, yeah. Is this clear? Okay, just 2-3 things I want to do before we stop for today. So we're going to have a class on Thursday, and we'll try to have an extra class next week as well. We'll try to complete our discussion of the heterotic string. We'll also try to complete our discussion of BRST current, and maybe even set up the rules for world sheet perturbation theory. And then we'll do lots of physics when we come back in June. Okay. Okay. So let's see. The first thing I want to argue for you is that this k has to be whatever, we don't know much about this k. Let's say this d is chosen to be positive definite. Okay, it's like proportional to delta function, not minus delta function. Delta AB, not minus. In that language, I'm going to argue that this quantity has to be positive. That this k hat has to be positive. Okay. Now, why is that? Well, I mean, this is just the usual story. Okay. Not if it's unitary. I'm going to use unitarity to show that it's. Yeah, Weisser-Witten k has to be positive. So 1, 2, 3, 4. Okay, and the basic idea is this. What we're going to do is to take the vacuum state, or the state proportional to the identity operator, and act on it with j minus 1 of A. Okay. Now I take the norm of this state. And if this thing is unitary, it must be positive. Okay. Now the vacuum state is the state that is the lowest energy in the theory. So it is annihilated by all j's with positive m. Okay. So, and of course, so we're just doing the usual thing. So this is JA1, JA minus 1. But I'm going to convert this into a commutator. This will be J1A, J minus 1A because the other term in the commutator annihilates the state. And then what I do is to use the commutation relation. Now since I started with A and A, the FABCD term gives 0 because this thing was symmetric. So all I'm left with is DAB times 1 minus 1, so that's 1 times k hat. Sorry, DAA times k hat, but this has to be greater than or equal to 0. Since we've assumed that DAA was greater than 0, that tells you that k hat is greater than or equal to 0. This is a positive definite kind of thing, inner product. So that tells us that k hat was greater than or equal to 0. Is this clear? So if you've got unitarity, at the moment we haven't said much about this k hat, but we've concluded that it has to be greater than or equal to 0.
This is true for any real state, not necessarily for the ground state.
What I used was the fact that this state was annihilated by J1A.
Oh, okay.
Because I converted this into this.
So it is also saying that every DA should have same sign.
What?
Every DAA should have same sign.
Every DA should have same sign. That's just the statement that this is a positive definite inner product.
Oh, positive.
Since it's a positive definite inner product, any vector times itself is positive. So in particular, you choose the vector delta A, vector known only there. Okay, so that was automatic because this was a positive definite inner product. Now what the new information we get is that k hat is greater than or equal to 0. Okay, great.
So is there any quantization condition on k hat?
Yes, there is. I'm going to show you immediately.
Because you got it labeled.
Yes. And now we discuss this quantization. Okay. Now what we're going to do is this. Suppose we have any root E plus minus alpha of our Lie algebra, the Lie algebra associated with FABC. I have an E alpha and the corresponding E minus alpha. Now let us remember that if I define J3 is equal to alpha dot h by alpha square, and if I define J plus minus is equal to E plus minus alpha,
The answer was the level k that we have,
that
that can be of any sign.
can be of any sign. But the Wessumino-Witten theory, I mean, if you want Wessumino, you see, Chern-Simons theory is related to blocks of Wessumino-Witten theory.
Yes.
Okay, these blocks you can define, that's an issue which is not associated with unitarity. But if you want this thing to be a nice unitary Wessumino-Witten theory by itself, this has to be positive. Also in Chern-Simons theory, k and minus k are sort of trivially related to each other by a parity flip. So there's no real information in one or the other.
I agree. So this is the thing that if one of them is allowed and the other one is related by a symmetry, not really a symmetry but
Yeah,
very simple orientation reversal
yes,
of the same space time.
same space time. But you know, you can relate each of them to a Wessumino-Witten. I think that the way it will work is that you know, the minus k will make things rotate the other way.
Yes.
Okay, so what it will be is that like a plus k will be related to a block of the holomorphic part, and a minus k will be related to a block of the anti-holomorphic part. Okay, but it won't. So it's the relationship with k itself. I mean, if you want unitarity, k is always positive in the Wessumino-Witten theory. Yeah, that's a good question. It would be nice to get clearer on that. Okay, now let's look at this. I take any alpha and I do this. Now it's a standard thing in group theory. In fact, I'm sorry. In fact, that was the thing, right? Anyway, let's forget about that. It's a standard thing in group theory to define, associated with any root, there is an SU2 subalgebra of the Lie algebra.
Yeah.
And the SU2 subalgebra I've just written down here. Call E plus J plus, call E minus J minus, and call J3 alpha dot h by alpha square. Okay, let's check that this is an SU2 subalgebra. Okay, so I'm going to compute J3 commutator J plus minus. Okay, so that is equal to alpha dot h by alpha squared commutator E plus minus alpha, which is equal to alpha dot alpha plus minus by alpha squared E plus minus alpha, using the fact that h with E alpha is alpha times E alpha, which is equal to plus minus E plus minus alpha. Okay, which is plus E plus minus J plus minus. The correct commutation relation for and similarly J plus J minus is equal to, if you remember our commutation relations that were written down there, is 2 J3, because it was 2 alpha dot h divided by alpha square. But here we just have alpha dot h divided by alpha square, which is also the correct commutation relation for J3. So it's a standard manipulation in Lie algebras that associated with any root, there is, and a particular Cartan associated with that root, there is an SU2 subalgebra. This is, by the way, used in trying to find, when you try to find representations. You use the fact that unitary representations of SU2 have the highest weight, all of that, highest and lowest. You use this a lot. Now, I'm just reminding you of this because we're going to use something very similar. What I'm now going to do is this. This construction we have, but I'm going to make a second construction. Consider alpha dot h plus k hat divided by alpha square. E alpha 1 and E minus alpha minus 1. I want to show that these three objects also satisfy the SU2 algebra.
This 1 and minus 1 below refers to the G1?
It's these.
Yeah.
Okay. What? Alpha minus alpha is any root. Okay. So once again we've got any root. It's minus root, but now instead of taking the 0, what we did here, the standard Lie algebra thing, is the same thing if we just put everything 0. H0, E1, 0 in. Here what I'm doing is H0,
But E1.
E1, E alpha 1 and E minus alpha minus 1. Okay, so it's
What is this? Full thing was not Lie algebra.
what?
The full thing.
Full thing was some complicated algebra, but I want to show that this satisfies its own closed Lie algebra.
What is this H0?
It's a subalgebra.
How do you know E alpha 1 is
What do you mean, how do you know? Every J1 exists. For every J, there's an M from minus infinity to infinity. E is just one of the J's.
What is the H0?
What?
H0.
H0 means H, the zeroth component.
J0.
J0.
Alpha.
Is this clear?
Yeah.
Okay. Now, let's look at the commutation relation of this with this and this with this. That's exactly the same algebra as here. Why? Because constant commuting with anything is 0. And here we got the same algebra because this term didn't click. Because we had 0, 1 or 0 minus 1. So this part, okay, this part, that J3 with J plus minus is equal to plus minus J plus minus is the same algebra as before. All that remains to be checked, is that J plus with J minus also works. So let's check that. So we have E alpha 1, E minus alpha minus 1. Okay? Now, again, this part the part coming without the k is the same algebra as before, because it just comes from the FABC, and we're going to get it with a 0. So that this part comes out right with the right 2 is obvious. What remains to check is the term with the k hat divided by alpha square. Okay? So that's entirely coming from here. So this is k hat d1 minus 1.
No, I think these are different indices. So these are different indices.
You're right, you're right. K hat d alpha minus alpha.
No, and alpha minus alpha doesn't also refer to plus minus, right?
No, it refers to this AB. Right, so this
Okay, I see, okay.
yeah, and then just this. We should really be looking at this this term here, and there was a 1, so it was this. Okay, but d hat alpha minus alpha is simply alpha square, right? So let's see, how does that work? It's basically, what does it mean?
You haven't written this answer in the standard form.
What?
Right now, the Lie algebra part is also not in the standard form.
Yeah.
This extension is also not in the standard form, but then you can put it in the standard form. That will have some coefficients.
Yeah, I was just wondering whether this by definition would be alpha square. Just because it's like the inner product of a d.
Last time it became 1 by alpha square because of this coefficient that you wrote. This particular basis. In case of Lie algebra, E alpha, E minus alpha indicators
Yes.
was alpha dot h by alpha square.
Yes.
That was this particular basis.
Yeah, he's saying that k doesn't have to be an integer, but 2k hat over alpha squared is an integer.
Sorry. But which basis?
Last time when you have Lie algebra, then you are calculating various commutators.
Yes.
In particular, you are calculating commutator between E alpha and E minus alpha.
Yes.
And that was set to equal to alpha dot h by alpha square.
Correct.
And that was some particular basis which has all these nice properties. Here as well, you will like to put this whole algebra in this nice basis.
Right. You're asking what is the value of d alpha in this?
The fact that d alpha minus alpha was order 1 by alpha square, even in Lie algebra, that was this proof that you didn't do. That was this particular basis.
Yeah.
Here something equivalent will go through.
Yeah. But just give. But wait. I can prove. If you allow me to, sorry. I want to show you that d alpha is the same as E alpha, E minus alpha. By definition, this is equal to d alpha minus alpha. Okay? I want to show you that this quantity is 2 by alpha squared. I want to prove that this is the case. Okay? And the way I'm going to do that is take this, that's what you're saying. Take the quantity E alpha, E minus alpha. E alpha, E minus alpha is equal to 2 alpha dot h divided by alpha square. Take this equation and take hi with each of these and put an hi with each of these and take trace. See, this is one of the manipulations we started doing. Okay, now we can remanipulate this guy to give an HI commutator E alpha E minus alpha. That gives an alpha I times E alpha E minus alpha. On this side, HI is 1. That's the assumption. The HI's are unit normalized. And then we get an alpha I here. So the alpha i's cancel. So that tells us that E alpha E minus alpha is 2 by alpha square. Okay, great. So then this quantity here, which was d alpha minus alpha, which is same as E alpha E minus alpha, was 2 by alpha square. And therefore, this term here, this piece is equal to 2k hat by alpha square, and so 2 times this. And so the SU2 algebra works.
By SU2 algebra, this J3 has to be quantized.
Exactly. Exactly.
In
Now,
half.
now this quantity by itself is J3 of some SU2 algebra, namely this one. But this quantity is also J3 of some SU2 algebra. Okay? Now, every J3 of an SU2 algebra is a half integer. Therefore, the difference between the two J3s has to be a half integer. Okay? Therefore, k hat has to be equal to a half integer times alpha square. Okay? Now, it's one of the facts of Lie algebra that Lie algebra is of two sorts. Either all roots have the same length, like for instance in SU2, or they have two different lengths. Yeah. When they have two different lengths, the ratio of the two lengths is 2. Alpha squared long root is twice alpha squared short root. Okay? So this condition is most stringent when alpha squared is a long root. Because if it's half integer times, did I get the other way around? If it's half integer, yeah, so suppose short root. Most stringent when it's a short root.
Yeah.
Okay? No. Long root.
It has to be long.
Long root. Because you see, if it's half integer times a short root, then it will be 1/4 integer times the long root, which is not allowed. It has to be half integer times both the roots.
Yes.
Okay? Therefore, it has to be half integer times long root. If it's half integer times long root, it's integer times short root, which is fine.
Yes.
Okay? And therefore, the condition we get that k hat is equal to half int times long root. Length of the long root square.
And then does that give you like some bosonic subsystems and some fermionic subsystems? Because if you have k hat being integer or half integer, or do you always make sure?
No, even level 1,
I just one comment.
Yeah.
Usually people choose this long root to be of length 2.
Yes.
So that k is an integer.
Yes.
Now you can be even integer or odd integer.
Yes.
And they
That's what he's asking. Yeah.
Even integer and odd integer Chern-Simons has very distinct nature. It will be fancy.
Spin manifold. I'm going to hear spin manifold in this discussion.
I understand the content that the number of inequivalent Wilson lines that you can write will be of different number. For example, if you are at U1 at level k, if k is an even integer, then you can write Wilson lines of charge 0 to k minus 1, 0, 1 to k minus 1. Kth one will be transparent, like you cannot detect its monodromies. Similarly, if k is odd, then it will go from 0 to 2k minus 1. It depends on if the one that you are considering, if it is transparent, that means that you cannot detect its monodromies, and also if it is trivial spin.
Yeah. These are these recent papers by Seiberg and company.
Yes.
That's what you're saying.
Without this word, this is the physical content, different number of Wilson lines.
Right.
Inequivalent Wilson lines.
Right. I'm just trying to think about the representation theory of the SU2, let's say, Weissomino-Witten algebra. I don't see a huge difference between. There must be, as you're saying, there must be. I don't really see a big difference, at least at the level of representation theory.
Are you imposing modular invariance?
Not yet. I'm just doing blocks.
So when you want to restrict, so right now your Young tableau has everything. Like it could be.
Okay. It's true that. You're probably right. There may be. I'm not completely sure I see it, but there may be a qualitative difference between odd and even half integer. You're probably right that especially if you try to define this thing on some more general manifolds, you might see it immediately. Right?
Yes, but even on R2, if you look at Wilson lines, which are inequivalent.
You're talking in terms of Chern-Simons theory, right?
Yes. Which will be sort of primary operators here and their dimensions.
Well, they'll just be the. I mean, at the level of primary operators, spectrum of allowed primaries is from 1 to k, irrespective, right?
In terms of the number of boxes in the interval.
Yes, irrespective of whether k is odd or even. The fusion rules don't care about whether k is odd or even. What?
Even for U1 there will be a difference.
There's some difference in some context.
You are looking at non-abelian gauge group, right?
I'm looking at the non-abelian gauge.
Even for the abelian gauge group.
Let's say I look at abelian gauge group. I'm saying just the representation theory, even for an abelian gauge group, is basically at the level of Weissomino-Witten algebra. I don't see a difference actually.
Yeah,
you're saying once you make a modular invariance, but modular invariance is irrelevant to Chern-Simons. Anyway, let's forget this right now. There's certainly maybe some contexts in which there is a difference. Yeah, because Chern-Simons only cares about one holomorphic part, right? Modular invariance doesn't come into that discussion. Anyway, let's forget it for now. Let's forget it for now. You must be right. Yeah. Okay. Oh my, it's 5 o'clock. Okay. Now, people normally call the length the long root psi, or the length of the long root psi square. So the way people write this is that k hat is equal to psi squared by 2. Is half integer times psi squared by 2, or more like 2 k hat divided by psi squared is equal to an integer. This integer is called the level of the Weissomino-Witten theory. This thing runs 1, 2, 3, 4, 5, 6. We've already seen it's positive in the unitary theory and goes to 1 to 3 up to infinity. Okay, I want to discuss also for you this what's called the Sugawara construction, and then I wanted to apply this to the heterotic string. But we'll do this on Thursday.